Hello, and welcome to our short lesson on the stable roommate algorithm, also known as Irving's algorithm, where we will explain to you how to match up pairs in a set of data based on their preferences. Stable matching allows us to pair up individuals in a group, finding the best couples for everyone within it based on who or what each individual would most like to be joined with. That sounds quite confusing, doesn't it? Why don't we start with some background? In 1962, David Gale and Lloyd Shapley showed that for two sets of data of equal size, a pairing can be found such that all elements within the set can be paired with a corresponding element in the opposite set. Each element has an order of preference of matching, and the pairing will make sure the best match is found for each one. This is the stable marriage algorithm. The stable roommate algorithm is similar, with one key difference. There is only one set of people. The pairs have to be found from within this set. This means there can be situations where a stable match cannot be found. Now here is the algorithm. It's split into three separate loops. The first loop makes sure that every person has at least one match. In other words, keep looping until everyone has proposed a match that's been accepted. However, it is possible for someone to be rejected by everyone. In this case, no stable match can be found. The second part checks to see whether any non-rejected pairs are obviously worse than the proposed match for a given person. We get rid of any possible pairs that the person ranks below the proposed match we're looking at. This ensures that each person will take the best match they can get. The third and final part checks for cycles within the remaining matches and removes the worst pairs until there is only one match per person, thus ensuring the best possible matches for everyone. These matches will then be your solution. This all sounds a bit tough, so let's try an example to clear things up. We'll work through each loop separately and explain their workings in more detail before each step of the example. Here is loop 1. First, the algorithm states that we keep going until all people are matched. At each loop iteration, we select the first unmatched person in the table. They attempt to match with their next possible choice. This can be either accepted or rejected. The pairing is accepted if the person they are proposing to has not been proposed to before, or the person they want to pair with finds them more desirable than their current match. Otherwise, the pairing is rejected, and that person will look for another match on the next loop iteration. Now, let's work through loop 1 on some example data.
Here is a group of people, A to F. They each need to be paired up as roommates and are given their order of preference of who they would like to live with. Firstly, we need to make sure that everyone has at least one match. We shall begin from the top and follow the algorithm. Person A would most like to live with person F, so we can show that F has been proposed to by A by underlining it like this. B is the next top person in the list without a stable match, so we match it with its first choice, A. Note, A has already been proposed to by somebody, and it has a match, but has not been proposed to itself. This means we can now show A has been proposed to by B by underlining it like so. C is next up, and would most like to pair with A. However, A has already been proposed to by B, so we must now look at A's preferences to see who it likes more. Turns out, A likes C better, so B is now rejected, and C is accepted. So now B is the top person on our list without a match, so we must go back to it. The first non-crossed out person is E, who has not been proposed to, so we can accept. Moving onwards to D, who would like to be paired with B, which is easy enough. E is next, whose favourite is once again A. A seems pretty popular. Looking at A, we can see that E is his least favourite, and definitely worse than C, so it's a straight up no. E's next favourite is B, who has been proposed to by D, so we must look at B to see who she would want more. Turns out it's E, so D is rejected. Back to D we go, who looks at E. E says no thanks because B is better, so D keeps searching. D's next target is A, who once again prefers another person, this time C, so once again D is rejected. D now looks at C, feeling quite desperate. Fortunately, C has not been proposed to, so is happy to accept. Finally, F, the only person to have not made a proposal, asks its top choice D. D has not been proposed to by anybody, so is happy to accept. And so ends step 1. Everybody has made an accepted proposal, so we can continue on to step 2. As we said earlier, the second part checks to see whether any matches we just found are obviously worse than another one for a given person. We get rid of any match that the person likes less than the possible match we're looking at. Our first accepted pair is between A and F, so we check F's preferences to see if there are any possible matches less preferable than A. B is less desirable, so can be rejected. Next up is B and A, which was rejected, so is not considered. C and A is accepted, so we look to see if there's anything worse for A than C, which there is not, so we cross out nothing. Now we look at B and E. E likes B more than F and C, so we can get rid of those pairings. Both D and B and E and A were skipped over as they have already been rejected. Now we look at E to B. B likes C less than E, so rejects C. Skipping through the next two, we come to D and C. There is nothing to cross off, as there's nothing worse than D. Same again here for F to D. There's nothing worse than F, so there's nothing to do. We have now gone through all the matches made in step 1, so finished step 2. As a reminder, the third and final part checks for cycles within the remaining matches and removes the worst pairs until there is only one match per person. A cycle exists if you can find a chain of people where you alternate adding the first person's second favourite match, the second person's least favourite match, and so on, until you return to a person already in the list. This then will be a loop, and the worst matches from the list can be removed. We now have to look through our list of people to see who still has more than one potential match. Our first is A, who could still match with F or C. We set A as P1 and write it in the table. We now look to see what A's second choice is and set it as Q1, which here is C. To work out what P2 is, we need to look at Q1's worst choice. C's least favourite is D, so that is our P2. Now we repeat the steps to find Q2, which is D, or P2, second choice. This is F. From F/Q2, we can find out P3. Looking across, we can see A is F's least favourite, so we write this in the table. Now look, we have a cycle. If we continue, we will repeat ourselves, so we stop here. We can now remove the pairs between each value of Q and its worst choice, i.e. Qi and Pi plus 1, as stated in the algorithm. With these removes, we can look again for the number of people with more than one potential match. This time, C is the first we encounter, so we write that as P1 and look for Q2. C's second choice is F, so that's our Q2. F's worst choice is C, so that's our next P, which already gives us a cycle, so we can remove F and C. Finally, we are left with only one possible pair for each person, which are A and C, B and E, and D and F, our solution.
If we look at the time complexities for each loop, we see the first loop is upper bounded by n squared, because there are less than n squared possible pairs, as seen in the table of preferences. The second loop is order n, as there can only be one match for each person. The final loop is also order n. There can't be more than n p-values, because of the n plus 1th p-value, there must be a cycle in P. As n squared is asymptotically greater than n, the overall order of the algorithm is n squared. And that concludes our tutorial. Thanks for listening.